Hello everyone, welcome to this talk about our recent paper, DS3, a system-level domain-specific system-on-chip simulation framework. This is a joint work from Arizona State University, the University of Arizona, Carnegie Mellon University and the University of Texas at Austin. Thanks to tremendous pace of Moore's law, the processing capability of integrated circuits drastically increased over the last 2 decades, paving the way for new domains of applications. Similarly, computing paradigms and architectures have changed, incorporating general-purpose cores and special hardware accelerators to meet performance and power requirements of these new applications. In the light of these developments, a research question arises. Can we quickly and accurately simulate emerging applications on new-age systems on chips? Driven by this research question, in this study, we developed a simulation framework that can perform design space exploration, evaluate scheduling and resource management algorithms. Our simulation framework, operating at system level, differs from full system simulation and hardware emulation, and provides the following advantages. First, DS3 is very fast compared to full system simulators, like Jam5, where simulation of even few milliseconds of workloads takes hours. Second, the controlled level of abstraction for both applications and target platforms enables rapid design space exploration. Furthermore, DS3 supports modifying existing scheduling and dynamic thermal and power management (DTPM) algorithms, as well as implementing new algorithms, and integrate them with the framework easily. Finally, DS3 provides a plug-and-play interface to choose between different scheduling and DTPM algorithms. The organization of the DS3 framework is depicted in this slide. The resource database contains the list of processing elements, PEs, including the type of each PE, capacity, operating performance points, among other configurations. By exploiting the deterministic nature of domain applications, the profiled latencies of the tasks are also included in the resource database. The simulation is initiated by the job generator, which generates application representative task graphs. The injection of applications in the framework is controlled by a user-defined distribution, for example, an exponential distribution. The DS3 framework invokes the scheduler at every scheduling decision epoch with a list of tasks ready for execution. Then, the simulation kernel simulates task execution on the corresponding PE, using execution time profiles based on reference hardware implementations. Similarly, DS3 employs analytical latency models to estimate interconnect delays on the SoC. After each scheduling decision, the simulation kernel updates the state of the simulation, which is used in subsequent decision epochs. The framework aids the design space exploration of DTPM techniques by utilizing these power models and commercially used dynamic voltage and frequency scaling (DVFS) policies. DS3 also provides plots and reports of schedule, performance, throughput and energy consumption to help analyze the performance of various algorithms. DS3 provides a set of commonly used built-in scheduling algorithms, which can be specified by the users in the main configuration file. We describe the built-in scheduling algorithms in DS3 using one of the most used canonical task graphs, shown on the left, before analyzing the results from real-world applications. In this task graph, each node represents a task, and each edge represents average communication cost across the available pool of PEs for the pair of nodes sharing that edge. The computation cost table, in the middle, indicates the execution time of the nodes on each PE. Then, DS3 framework generates Gantt charts to visualize the generated schedules. This allows the end user to understand the dynamics of the scheduler under evaluation. DS3 comes with 6 reference applications from wireless communications and radar processing domain. The Wi-Fi protocol consists of transmitter and receiver flows as shown on the left. It has compute-intensive blocks, such as FFT, modulation, demodulation, and Viterbi decoder, which require a significant amount of system resources. DS3 also includes a simpler single-carrier protocol, with a lower bandwidth and latency requirements. Finally, the framework has 2 applications from the radar domain, as part of the benchmark application suite, 1, range detection and 2, pulse Doppler, which are shown with the block diagrams on the right. DS3 enables comparing performances of schedulers for streaming domain applications under a target SoC. In this case study, heterogeneous SoC under consideration is consisted of 16 general-purpose cores and hardware accelerators, as shown on the table left. In addition, a wide range of the workload scenarios with domain-specific applications are considered by sweeping the application injection rate. As seen on the figure right, scheduling algorithms exhibit different trends of average execution time. Thus, DS3 helps user to determine the scheduling algorithm that is most suitable for a given SoC architecture and set of workload scenarios. For the DTPM case study, the same SoC configuration from the previous case study is utilized. The study explores 8 frequency points for the big cluster and 5 for the little cluster, using a 200 MHz step. All possible DVFS modes were evaluated, that is, all possible combinations of power states for each PE, in addition to on-demand, power save, and performance modes. The figure on the right shows the Pareto frontier for all configurations. The on-demand and performance policies provide low latency, with high energy consumption, while power save minimizes the power at the cost of high latency, which results in suboptimal energy consumption due to an increase in the execution time. The best configuration in terms of energy delay product, shown as green star, uses 1.6 GHz in 4 active cores for the big cluster and 600 MHz in 3 active cores for the little cluster. The final case study illustrates how DS3 can be utilized to identify the number and types of PEs during early design space exploration. The study employs the benchmark applications to explore different SoC architectures. All configurations in this study have 4 big ARM-A15 and 4 little ARM-A7 cores to start with, and DS3 guides the user to determine the number of configurable hardware accelerators in the architecture. In a grid search, the study varies the number of instances of FFT and Viterbi decoder accelerators. The table on the left lists the representative configurations out of 20 configurations. Each row in the table represents the configuration under investigation, with an estimated SoC area, average execution time, and average energy consumption per job. The figure on the right plots the energy consumption per job as a function of the SoC area. As the accelerator count increases in the system, the energy consumption per operation decreases. This comes at the cost of larger SoC area. For this specific workload, configuration 3, that is, an SoC configuration with 2 FFT and 1 Viterbi decoder accelerators, provides the best trade-off. As demonstrated in this study, the DS3 framework provides metrics that aid the user in choosing a configuration that best suits power, performance, area, and energy targets. In this slide, a short demonstration of a scheduling case study is provided, where different workloads with varying injection rates for an SoC configuration are executed with 2 of the built-in schedulers. The demo shows that the DS3 framework executes these workloads and plot a figure at the end to compare the schedulers in terms of average execution time. As a summary, we developed a Python-based system-level simulation framework, DS3, for domain-specific systems on chips that enables the comparison of different scheduling algorithms, evaluation of dynamic thermal and power management techniques, and extensive early design space exploration. The framework is calibrated against 2 commercially available platforms, which are Odroid XU3 and Zinc CCU102, with an average error of 5% for all cases. We envision that DS3 will pave the way for an easy and rapid exploration of domain-specific systems on chip, and to this end, DS3 is an open-source tool and can be accessed via the link below. Finally, this work is sponsored by Air Force Research Laboratory, AFRL, and Defense Advanced Research Projects Agency, DARPA. For more details, please take a look at our article and download the code to conduct similar studies. Thanks for listening.